In this problem, we're looking to find a magnetic field using a Hall probe. So in a Hall probe, we have a current flowing through a conductor. In this case, the height of the conductor is h, and there is a magnetic field that we're trying to determine. Keep in mind that the direction of current by convention is the direction in which positive charge move. We know the electrons are the one that's moving in the opposite direction with velocity v. Therefore, the magnetic force on the electron is as shown here in our figure, sort of into the page. So electrons will move towards the inner edge of the probe, leaving positive charge on the outer edge. This then creates a potential difference and therefore an electric field between the opposite sides of the Hall probe. The electric field is given by the voltage difference, which is referred to as the Hall's voltage divided by the separation of the charge. In this case, this would be the width of the conductor. The electron then will experience an electric force shown by the blue vector here, which is in opposition to the magnetic field. Eventually, these two will be equal and opposite, and there will no longer be a separation of charge. In this case, the magnetic field is given by the electric field divided by the speed of the electron. Okay, since the electric field can be written in terms of the Hall voltage, which would be V delta V over the width divided times the speed of the electron, then we can find the magnetic field B. Now, what is the speed of the electron flowing through the probe? Well, that will be dependent on the current through the probe. Current again is the number of charge flowing per second. This can be written in terms of the number of charge per volume times the size of one charge, times the speed of the charge, times the area of the conductor. In this case, the area A is highlighted in yellow, and we know the elementary charge, we know the current, we're looking for the drift speed. What is the charge density? This has been worked out for us for copper back in chapter 25, example 25.1. This is assuming that there is one free electron for every copper atom, and knowing the density of copper, we can then determine how much electrons we have per cubic meter. Then we can solve for the drift speed. It's sort of cut out there, but you can solve for drift speed with a little bit of algebra. We plug that back into our equation for the magnetic field, and since the area here is the height times the width, we can plug that in for A, and therefore we would have both widths on the numerator, the denominator, those two cancel out. So all we need to know then would be the height or the thickness of the Hall probe to determine the magnetic field. We know the current I, we know the Hall voltage is 0.25 microvolts. We now know what the number of charge carriers are per cubic meter and the elementary charge. You can plug that in to determine the magnetic field um, in which the probe is inserted in.